Stars, burning hot balls of gas and dust. Start out with a little bit of a review here. About 15 billion years ago, remember, the universe went bang! And then it laid the foundations for everything that we have today. We had our stars 10 billion years ago, our sun roughly 4.5, 5, so on and so forth. Here's an awesome picture of our galaxy, which you can see 100 light years is a distance. It's about 100 light years in diameter. You can see our sun is situated right over here, so we revolve around our sun, and the nucleus is just the center of the galaxy. So we had to talk about the Big Bang because it plays a huge role in the Doppler effect. The Doppler effect was proposed by Hubble, same guy with the Hubble telescope. Alright, so he's saying that a change in wavelength of light, depending on whether it's coming toward us or moving away from us. So the color will change, okay? So if something appears red, here I'll use my red color, that means it's moving away because red is a longer wavelength of light. Remember our Roy G. Biv, red being our longest wavelength, violet being our shortest wavelength. So if it has a blue shift or ending towards the blue end of the spectrum, that means it's coming towards us because the shorter wavelengths can reach us. And everything in our universe has a red shift, meaning everything in the universe is constantly moving away from us. So this picture here is demonstrating the Doppler effect. So we have our blue shift, our shorter wavelengths of light as the object is coming towards us, our red shift or our longer wavelengths of light as the object is moving away from us. Alright, so stars are humongous balls of glowing hot gases. The gases are hydrogen and helium, and they produce their energy by nuclear fusion. So nuclear fusion in the star is where hydrogen is changed to helium in the core. The life cycle of a star begins with a nebula, which is the birthplace of a star or a stellar nursery. It's called all those things. Okay, so this is a cloud of dust and gas in space. From a nebula, it will go to a protostar, which is a young star, no fusion yet. From a protostar, we'll go to a main sequence star. So this is the longest stage of a star. It lasts about 10 billion years, and this includes our sun. So what happens next depends on the size of the star. Is it humongous, or is it smaller, or is it medium-sized like our sun? So here are two really cool pictures of nebula, or clouds of gas and dust out in space, right? So here we have an Eagle Nebula, named as such by the wings, and then here's a Cat's Eye Nebula. Alright, finishing up the life cycle. So if you are a smaller star, this is how it will end its life. It will, after the main sequence stage, it will become a giant, which is, it will grow in size, but the surface itself will cool. And then it will become a white dwarf, which is much smaller but very, very hot. And from a white dwarf, it will turn into a black dwarf where it actually runs out of energy and dies. So just to compare sizes of a main sequence star, here's the sun in its main sequence stage. And then when it, the next phase of its life is a red giant, you can see how big it gets. Alright, here is a white dwarf here in the center of a nebula. So it is white, much hotter, smaller, very small. Alright, if you're a bigger star from your main sequence, you will then become a supergiant, which is really, really, really big. From a supergiant, you could do a couple different things. You could supernova and explode. Okay, so after a supernova, a very dense star will form as this gravity kind of pulls everything back together. That's called a neutron star. Or what could happen is after the supernova, particles come together, form this really, really strong gravitational force that we call a black hole. So there is a picture of a supernova, or what they think a supernova would look like. Alright, super cool. So there's this infrared image that NASA's Space Telescope took, and here we're looking at the center of the Milky Way galaxy, and so old cool stars appear blue, and hot, hot, hot things are red, really, really hot things are white. So they hypothesized that in the center of our galaxy is this black hole, a supermassive black hole. All right, a diagram showing you the two paths. Remember, so we have our stellar nursery, and then which will give way. The only step it's missing is the protostar here, and then you can be the sun-like star, a huge star, or a giant star, and that all, depends on your size. So the rest of your life is determined by your size. If we were going to compare it to the life of a human, protostar is when you're in the womb. Infancy through adulthood is your main sequence stage. You're getting a little bit older. Middle-aged is your red giant, supergiant. All right, a little bit older, you're going to be the white dwarf, black hole kind of area. All right, so here's a video that'll kind of show you the life cycle of a star with some cool pictures.
They begin in clouds of dust and gas so far away that we would need 100,000 years to reach them. Gravity gathers hydrogen gas and particles of dust, and the clouds grow more dense. Squeezed tighter, the hydrogen heats up to a fantastic 10 million degrees Celsius. Nuclear fusion turns hydrogen into helium, and the fire ignites. A star is born. Astronomer Michael Scharrer compares a star's life cycle to our own.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act, because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart.
Of course, a star may live for billions of years, and stellar age has nothing to do with lifestyle or heredity. It's all about size. Smaller stars burn cool and dim. When their fuel burns out, they just fade away. A medium star, like our Sun, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core harder, the star grows hotter and the outer layers puff up, engulfing nearby planets in its fiery demise. Finally, the outer layers blow off into space and a dense solid core remains. This white dwarf is a dying star. A bigger star, say twice the weight of our Sun, lives hot and dies young. It burns through its fuel in just millions of years, and it doesn't go quietly. There's more material here for gravity to constrict. The star goes out with a bang called a supernova. Gravity packs the remains into material far denser than white dwarfs, called neutron stars. A teaspoonful of this stardust weighs more than a cruise ship packed with people. Some enormous stars that have gone supernova become so dense they turn into black holes. Think about it. A massive explosion leaves gravity unchecked, and matter is squeezed into something unseeable, stretching for miles, and weighing incomprehensible amounts. Got it? Invisible but deadly, pulling in matter all around it. Even light can't escape. Not to worry, supernovas are rare. A galaxy like ours, of 100 million stars, may experience only one exploding star in a century.
So we're good to go. All right, last but not least, we have star color. So the star's color is based on its surface temperature, and from coolest to hottest, these are the colors. So red being the coolest, blue is the hottest, orange, yellow, and white in the middle. All right, apparent magnitude of a star is the brightness of the star as it appears from Earth. So apparent appears from Earth, okay? This is affected by distance, size, and of course color. So an absolute magnitude is the true brightness of a star. All right, so here we have the Hertzsprung-Russell diagram, which compares temperature and absolute magnitude, or the true brightness of the star. So here along our x-axis, we have temperature, and actually as it goes this way, the temperature is decreasing. And luminosity is on your y-axis, or brightness, and as you go up here, the luminosity or brightness is increasing. Okay, so our brightest and hottest stars are actually going to be our blue giants, whereas our coolest and dullest stars are going to be down here, these main sequence. So then what's a red supergiant? Well, it's cooled off a lot, but it's really bright. So you can kind of see where I'm going with this.